Now let's look at the release phase of our inductor. The inductor is storing energy during the storage phase, and it's holding on to that energy during the steady state. So when we want to release that energy back through the circuit, notice what happens if we were to open the switch. We would see this inductor trying to force that same current back through the circuit, and then there's no path for it to go. So that creates a problem. So what we want to do is redesign the circuit so that we give our current a path to release. So that's what we're going to see now is a circuit that has that path that we can release the energy back into the circuit. So when we close the switch, we are storing energy. So remember, as our voltage source is trying to establish a current, the inductor will push back against it a little bit until the point where there's the magnetic field's no longer growing, and you're going to see all of that current through the inductor at that point. So the current through the inductor at its maximum after it's reached that steady state is just going to be E over R1, because at this point the inductor looks just like a short circuit when we reach steady state. So, however, when we go to release that energy and we open the switch, we're then going to force that I sub L, or E over R1, back up through R2 and through R1 and so on. Okay, so this will be the path for current. So let's look at that circuit and what's going on. So we have, when we open up that switch, whatever I sub L is, the inductor is going to continue to push through that I sub L, that current, IL, not I2. And that's going to be the current through R2 and the current through R1. So notice for R1 that really doesn't change anything. Before we opened the switch, we had I sub L going through R1 this way. That gave us a voltage drop of VR1, so that's really not any different. What is different here is the voltage drop through R2. As our current is coming through R2, it's going to give us a voltage drop in that upward direction, which is opposite from what we saw over here. Back over here, when the switch was closed, you had R2 in parallel with E. So we had a voltage drop there that was VR2. Now, that voltage drop is controlled by I sub L. And so VR2 now is going to be in the opposite direction, and it's going to be IL times R2. VR1 is going to be IL times R1. And then what does that mean for V sub L? Well, let's look at Kirchhoff's current law, Kirchhoff's voltage law here. Okay, so KVL tells us that if we have a voltage drop of VR2 and a voltage drop of VR1, then we must have a voltage rise of VL, and that all has to equal 0. So that tells us that VL is actually VR1 plus VR2. So we're going to see a very significant change in voltage here, because remember, before the release phase, our inductor was a short circuit and VL was 0. Now we're going to see a very big surge of voltage in the opposite direction from where we started. So let's look at this problem. We're going to look at this problem in our notes. And we'll go back and look at the graphs in just a moment. So the release phase equations, let's talk about that. First off, we need to find our tau, or our time constant. So remember, tau is equal to L over R. Now in the release phase, when we open up this switch right here, our circuit is this one, and the effective resistance as seen by the inductor is R1 plus R2. So L is going to be 4 henries divided by the 3K plus the 2K ohm resistor. So that gives us 800 microseconds, meaning it's going to take 5 times that amount of time in order to release that energy back through our circuit. Okay, so let's look at what everything is doing in the circuit. In the release phase, everything goes to 0. What does that mean? It means everything has the shape e to the minus x. Okay, all the equations. So I sub L, we've got VR1 and VR2 in this case, and VL also, VL. All of these quantities are going to go from a maximum to 0, so e to the minus t over tau, and tau is 800 microseconds. So I'm just going to go ahead and plug all that in. And then we're going to figure out what those maximums are, because that's what we're going to put in front of this in our equations, is what that maximum would be. Okay, so yeah, we need the maximum VL, the maximum VR2, the maximum VR1, and the maximum current through our inductor. So let's just talk through this for a moment. I sub L is going to be whatever it was that we reached in steady state. So in steady state, keep in mind, in steady state, that was when we had the switch closed in this direction. And what would IL be? Well, think about it this way. When the switch is closed and we're in the storage phase, the 3K ohm resistor is in parallel with the 50 volt source. So I'm going to have 50 volts there. When we reach steady state, this inductor is going to look like a short circuit. So I'm essentially going to have the 2K ohm resistor in parallel with the source as well. If you want to draw that out and kind of prove to yourself that that's true, go right ahead. So that means that I sub L is really just going to be the 50 volts divided by the 2K ohm resistor, which is 25 milliamps. Why is that? Because you have 50 volts here across 2K ohms of resistance. Ohm's law gives you that you have to have 25 milliamps through that resistor. That's in series with your inductor, so it has to be the same current. So what we've said is we've got 25 milliamps here through the inductor. Now, that, as it turns out, when we go into the release phase, that is the most important thing to know, is that the current right before we open that switch was 25 milliamps. Okay, so I'm going to get rid of everything here, and I'm going to make a note again that when we open that switch, right at that moment, we have 25 milliamps, and then over time, that's going to go to 0. Okay, so in about 4 milliseconds, it'll all be over, and that'll be 0. Okay, but what does that mean? If I have 25 milliamps through this circuit, I've opened the switch, so that means that 25 milliamps is going to go this way. And then it's going to continue this way, 25 milliamps. And so on, right? So I've got 25 milliamps initially until I start to release that energy a bit. And that's going to determine my voltage drops, right? Because if I have 25 milliamps through 3 ohms of resistance, that means I'm going to have 75 volts drop across that R2. So VR2, and this is at t equals 0, okay, right when I open that switch. We've got 25 milliamps through 3 k ohms of resistance, so I've got 75 volts there. What about VR1? Again, I've got 25 milliamps of current through the resistor, which is 2K in this case, so 50 volts. And if you recall, that's what we had in the storage phase. We had 50 volts there. So, VR1 is going to be 50 volts. It's going to start at 50 and go to 0 over time. And now let's look at VR2. VR2 is 75 volts. We just calculated that. But remember, it's in the opposite direction from where it was in the storage phase. So I'm not just going to put 75. I'm going to actually say negative 75. Okay? Because that just indicates that the direction is different from where we started. Okay, it's not really a negative voltage so much as it's the opposite direction that we're talking about. So then I have to figure out what's going on with V sub L. Okay, when I was at the steady state, VL was 0 because the inductor looks like a short circuit. So at this point, I'm going to have a voltage drop because I've got a voltage drop of 75 here, a voltage drop 75 there, a voltage drop of 50. So I'm going to have a voltage rise in this direction of what? Well, KVL says that if I have a voltage drop of 75 and a voltage drop of 50, I have to balance that out. Okay? So that means that VL would have to be 125 volts. That's a lot. When you just started out at 50 volts with the source, and now you've got a spike of 125 volts, and as it turns out, that's in the opposite direction as well, so I'm going to call that negative. Okay, let's just look at these graphs, and this will kind of show you what we're talking about here. So this VL that I was telling you about, that's right here. So in the storage phase, remember, in the storage phase, that inductor is pushing back against the voltage source that created it. So it's initially an open circuit that becomes a short circuit. So we're starting at our maximum of 50 volts and going to 0 in the storage phase. When we get to the release phase, we're going to see a spike in the opposite direction of 125 volts that's going to quickly go to 0. Now let's look at I sub L. Now I sub L, in the storage phase, we started at 0 because the inductor does not want the current to change instantaneously, so it's going to try to keep it at 0 for a little while, and then once that magnetic field stops growing, we see that we're at our maximum current at that point, and then the inductor looks like a short circuit, and if we didn't open the switch, it would stay at that 25 milliamps indefinitely. However, when we open the switch, the current's going to try to keep that 25 milliamps for a bit, but it's just going to drop down as it releases that energy, and that's what's going on in the release phase. For VR1, right here, VR1, notice it looks exactly the same as the current. Why is that? Because the current IL is the current through R1, and they're related via Ohm's law. So really, it's just going to be different numbers. So you've got 25 milliamps here, and this is 50 volts. So it's really just separated by a factor of 2 kiloohms. So those are just an Ohm's law relationship away. Now, R2 is a little bit different. R2 is kind of interesting to look at. For R2, remember when we closed the switch and we were in that storage phase, R2 really wasn't involved in that. R2 had 50 volts across it, and it really didn't matter what the inductor was doing, because since R2 is in parallel with the source, it had 50 volts across it, and that didn't change. It wasn't time dependent. So you see in this storage phase for VR2 that it was just at 50 volts that whole time. It never changed. But as soon as we opened the switch, we saw that it spiked to a 75 volt rise in the opposite direction, and then went to 0. So in the release phase, absolutely everything is going to 0. So everything has the same equation. The trick is just figuring out those voltages. Okay. So let's look at another example here. And we'll write the release phase equations for our circuit here. Okay, so in order to do that, we need to know what IL is in steady state. Okay, because that's going to determine what happens in the release phase. So we do need to understand that. So first thing we want to do is imagine that we're in that storage phase, and we're going to kind of ignore R2 for a moment. I mean, basically R2 is in parallel with the source, so we've got 36 volts there, and we've got, so it's basically like we have 36 volts applied to our second branch over here. So if we want to know what IL is in steady state, it's basically going to be at the point when we have a short circuit here, and we've got 36 volts across the 100 ohm resistor in series with the 20. Okay, so that's going to be 36 volts divided by 100 plus 20 ohms, 120 ohms, which is about 300 milliamps. So that's important to know. Okay, now let's talk about the time constant in the release phase. It's a little different in the storage phase, but in the release phase, when we open this switch back up, again, imagine the path of that current. It's going to go this way. So the resistance we're going to use in this equation would have to be R1 plus R2 plus R3. So remember, it's L over R, and in this case, L is 0.6 henries, and the total resistance here is going to be the 100 plus 470 plus 20, or 590 ohms. So tau of the release phase will be about 10.17 milliseconds. Okay, once we've found that and we know what our steady state current would be, at this point we are ready to write some equations. Okay, so let's look at I sub L, for instance. That's kind of an easy one, because basically I sub L is going to start at the current it was at when we entered the release phase, and it's going to release that energy back through the circuit in 5 time constants. So we're going to go from a maximum of 300 milliamps down to 0. Okay, pretty simple there. VR1 and VR3 are pretty much going to be the same voltage they were when they started the release phase as well. So what we're going to see there is that 300 milliamps times R1 will give us VR1. And 300 milliamps times R3 will give us the maximum voltage there, the voltage that we're starting with. Okay, so for VR1, we're looking at about 30 volts, e to the minus t over tau. And for VR3, we're looking at about 6 volts. And now let's look at VR2. So when we were in the storage phase and steady state, we had a voltage drop of 36 volts across R2. But in the release phase, that's no longer true. It's not in parallel with the source anymore. What is going to determine that voltage drop is this 300 milliamps of current coming from that inductor that's trying to keep the 300 milliamps of current going through the circuit in the same direction. So that voltage drop is going to be our 300 milliamps times 470 ohms. And again, the same shape of the curve, because whatever voltage we're starting at, we're going to 0 after this. Turns out that's about 177 volts. That's a lot. Oh, actually, it's 141, sorry. 141. Okay. So that's where we're starting. So I'm going to draw these in. I'll put green here. So we've got a drop of 141 volts initially, a drop of 30 volts, and a drop of 6 volts. Okay, so how do we find what VL would be? So VL at this point is going to be the sum of the voltage drops around that closed loop. So 6 plus 141 plus 30. So that will be 177 volts initially. So remember, VR2, that was in the opposite direction. Remember, in the storage phase, we had 36 volts in this direction. In the release phase, we have 141 volts drop in the opposite direction. So I'm going to use a negative sign to denote that's in the opposite direction. The 30 and the 6 for VR1 and VR3 is exactly the same direction. So for VL, again, we're going to start at a maximum and go to 0. And that maximum is actually 177 volts in the opposite direction. So again, anytime after you open that switch, we can plug in a time and actually calculate the current, the voltage drop across either of any of the resistors, and the voltage drop across the inductor at that time. Okay, let's just spend a moment on combining inductors. If you have multiple inductors in the circuit, you're going to combine them exactly like you did resistors. Okay, so for our series inductors here, we're going to add, and then those series inductors, 12 henries there, 6 henries here, and 6 henries here. These are now in parallel, so we're going to combine those like we would parallel resistors. So that would be 4 henries. And then that 4 henries we would add to the 6. So this would be 10 henries total. So we combine inductors like resistors. Okay, remember the capacitors, we're going to combine those the opposite way we did resistors, but for inductors, they're combined exactly the same way. So for our part B, I'm going to combine our two 4 Henry inductors. They're in parallel. So that means we have that 4 Henry inductor from up here, and this becomes 2 Henries. And we've got, whoop, that's not a resistor. And here we have a 4 Henry inductor as well. So these combine, we've got 6 Henries here. So if we combine the 6 and the 4 in parallel, and 2.4 Henries. Okay, let's work on the next two. Again, if you want to try it yourself, just pause the video and you can do this yourself. Here, remember, so we've got capacitors we're going to combine and inductors, so we'll be left with 1 inductor and 1 capacitor at that point. So here, if we combine our capacitors in series, remember, it's like parallel resistors. So that's 9 microfarads, which we would then add okay, so our total capacitance is just 18 microfarads. Here we're going to combine these like we would parallel resistors. They're parallel inductors. So we've got 10 millihenries there. And then we're going to add that to our 6 millihenries. So LT equals 6 plus 10, or 16 millihenries. So that means if we were to redraw this in the simplified form, we would see 16 millihenries and 18 microfarads. How about what's going on with this one over here? We've got the 7 and the 42. And those are in parallel. Okay. But remember, we combine those like we did. No, those are, I'm sorry, those are in series. I'm sorry. If you had that right and I just confused you, I'm sorry. 7 microfarad and 42 microfarad in series mean that we combine them as if they were in parallel for resistors. So 1 over 7 plus 1 over 42 means that we have about 6 microfarads there. And then once we combine those, that'll be in parallel with my 12. So plus 12 microfarads. So what that gives us is something like this. You've got your 12 microfarads in between the 20 millihenries and the 5 millihenries. And since these are in series, we can really shuffle them around a little bit so that we combine the inductors. So I've still got the 12 microfarads here, and we've got 25 millihenries there. And this is the simplified version. Okay, so go back through that and practice if you